Physics graduate programs teach the quantum harmonic oscillator as a fully solved system. It serves as the unquestioned mathematical bedrock of all quantum field theory. The standard approach relies on algebraic notation. Using the creation and annihilation operators formalized by Paul Dirac, physicists can generate discrete energy levels and populate a Fock space. While this algebraic formulation is highly effective for rapid calculation, it obscures the geometric reality driving the system. Relying solely on abstract operators leaves us blind to the physical architecture of phase space. To understand how quantum mechanics actually operates, we have to look at the geometry the algebra is hiding. We can translate the harmonic oscillator from pure algebra into rigorous geometry using the complex Barkman-Fock-Segal representation. This framework suggests quantum mechanics is a specific type of abelian gauge theory operating directly on phase space. This visualization maps the wave function as a holomorphic section within a structured complex line bundle. The classical phase space serves purely as the flat base manifold. The quantum states themselves exist entirely within the fibers extending vertically above it. In this model, quantum states are precise geometric structures interacting with a background field. We begin by defining the classical phase space using dimensionless complex coordinates to map position and momentum on a two-dimensional flat plane. We construct the extended phase space bundle, denoted as L sub v, by extruding a vertical complex fiber straight up from that classical base plane. Before jumping to full quantum mechanics, we can define an almost quantum oscillator, a theoretical state where a single particle moves through this three-dimensional extended space. This allows us to pinpoint the ground state. On the classical base plane, the particle is strictly at rest at the origin. However, within the internal complex fiber, it possesses constant motion, rotating along a circular path. The entire dynamic reality of the ground state exists exclusively within this unobservable internal fiber, making it invisible to classical mechanics. That rotation within the fiber has a specific angular velocity. This rotation is the physical and geometric source of the oscillator's zero-point energy. This rotational energy curves the total space of the bundle, generating a constant background curvature field. Crucially, this massive zero-point energy curves the quantum bundle above while leaving the underlying classical phase space flat. This geometric curvature maps directly to the algebraic foundation of quantum theory, the canonical commutation relations. Fundamental non-commutativity is a direct measurement of the quantum bundle's geometric curvature. To analyze the excited energy states, we remove the zero section, the ground state, from the bundle, leaving us with a punctured geometric space. Using geometric invariant theory, we see that this punctured bundle is biholomorphic to a conical orbifold structure containing a spherical submanifold. Zooming into this internal geometry, we find a particle moving along a circular path within a lens space embedded inside the orbifold. This excited state describes a classical invariant motion. It completes its cycle at a strict multiple of the ground state speed. The specific energy level of the excited state dictates the precise angular velocity of this cyclical path. Energy level n simply means the particle rotates n times faster. Each excited quantum state mathematically encodes a specific cyclical classical trajectory trapped within a hidden geometric lens. We cross the threshold from almost quantum to true quantum when we stop tracking a single point and begin tracking an entire global section. Evaluating a global holomorphic section requires mapping the entire space of possible initial data simultaneously, rather than following one isolated trajectory. Mathematically, this global section takes the shape of a Riemann sphere, embedding itself directly into the geometry of the bundle. The entire embedded sphere rotates as a single unified geometric object. The distinct punctures on this rotating sphere are the zeros of the polynomial, known in applied physics as Majorana stars. The true quantum state emerges from the synchronous rotation of an entire geometric manifold of initial conditions. We can now redefine the standard algebraic ladder operators. Geometrically, these are covariant derivatives. Moving between quantum energy states requires physical interaction with the constant background gauge field. The covariant derivative utilizes the connection to translate the section up or down the bundle's structural hierarchy. This behaves exactly like a charged particle moving through a magnetic field. Quantum state transitions are purely gauge interactions. Changing energy levels is a literal shift in geometric position driven by a background field. In superposition, the particle acts as a reducible representation, grouping an infinite number of classical trajectories into a single Hilbert space. Fixed quantum numbers cannot be assigned while the particle exists in this mixed, reducible state. Measurement acts as an external gauge interaction that forces this reducible cloud to project onto a single, irreducible geometric slice. This interaction attempts to shift the complex fiber's point of attachment down into the classical phase space. The bundle's intrinsic curvature resists this shift. That resistance enforces a rigid limit on precision, generating Heisenberg's uncertainty principle. This geometric framework extends far beyond the harmonic oscillator. Using Kusta-Hamo-Stiefel regularization, we map the classical Kepler problem into this exact same bundle geometry to accurately describe the hydrogen atom. The boundary between the classical and the quantum is defined by a sharp geometric transition, a move from tracking points in phase space to tracking global sections in a gauge field.